Chapter 42, Crash Consistency, FSCK and Journaling. As we've seen thus far, the file system manages a set of data structures to implement the expected abstractions, files, directories, and all of the other metadata needed to support the basic abstraction that we expect from a file system. Unlike most data structures, for example, those found in memory of a running program, file system data structures must persist, i.e., they must survive over the long haul, stored on devices that retain data despite power loss, such as hard disks and flash-based SSDs. One major challenge faced by a file system is how to update persistent data structures despite the presence of a power loss or system crash. Specifically, what happens if, right in the middle of updating on-disk structures, someone trips over the power cord and the machine loses power, or the operating system encounters a bug and crashes? Because of power losses and crashes, updating a persistent data structure can be quite tricky, and leads to a new and interesting problem in the file system implementation, known as the crash consistency problem. This problem is quite simple to understand. Imagine you have to update two on-disk structures, A and B, in order to complete a particular operation. Because the disk only services a single request at a time, one of these requests will reach the disk first, either A or B. If the system crashes or loses power after one write completes, the on-disk structure will be left in an inconsistent state. And thus, we have a problem that all file systems need to solve. How to update the disk despite crashes. The system may crash or lose power between any two writes, and thus the on-disk state may only partially get updated. After the crash, the system boots and wishes to mount the file system again, in order to access files and such. Given that crashes can occur at arbitrary points in time, how do we ensure that the file system keeps the on-disk image in a reasonable state? In this chapter, we'll describe the problem in more detail and look at some methods file systems have used to overcome it. We'll begin by examining the approach taken by older file systems known as FSCK, or the file system checker. We'll then turn our attention to another approach known as journaling, also known as the write-ahead logging, a technique which adds a little bit of overhead to each write, but recovers more quickly from crashes or power losses. We will discuss the basic machinery of journaling, including a few different flavors of journaling that Linux ext3, a relatively modern journaling file system, implements. 42.1, a detailed example. To kick off our investigation of journaling, let's look at an example. We'll need to use a workload that updates on-disk structures in some way. Assume here that the workload is simple, the append of a single data block to an existing file. The append is accompanied by opening the file, calling lseek to move the file offset to the end of the file, and then issuing a single 4KB write to the file before closing it. Let's also assume we are using standard simple file system structures on the disk, similar to file systems we have seen before. This tiny example includes an inode bitmap with just 8 bits, 1 per inode, a data bitmap, also 8 bits, 1 per data block, inodes, 8 total numbered 0 to 7, and spread across 4 blocks, and data blocks, 8 total numbered 0 to 7. Here's a diagram of this file system. If you look at the structures in this picture, you can see that a single inode is allocated, inode number 2, which is marked in the inode bitmap, and a single allocated data block 4, also marked in the data bitmap. The inode is denoted I brackets V1, as this is the first version of this inode. It will soon be updated due to the workload described above. Let's peek inside this simplified inode too. Inside of I V1, we see owner Remzi. Permissions read, write. Size 1, pointer 4, pointer null, pointer null, pointer null. In this simplified inode, the size of the file is 1. It has 1 block allocated. The first direct pointer points to block 4, the first data block of the file, DA, and all 3 other direct pointers are set to null, indicating that they are not used. Of course, real inodes have many more fields. See previous chapters for more information. When we append to the file, we are adding a new data block to it, and thus must update 3 on-disk structures, the inode, which must point to the new block and record the new larger size due to the append, the new data block DB, and a new version of the data bitmap, call it BV2, to indicate that the new data block has been allocated. Thus, in the memory of the system, we have 3 blocks which we must write to disk. The updated inode, inode version 2, or I brackets V2 for short, now looks like this. owner Remzi, permissions, read write, size 2, pointer 4, pointer 5, pointer null, pointer null. The updated data bitmap, B brackets v2, now looks like this: 0, 0, 0, 0, 1, 1, 0, 0. Finally, there is the data block db, which is just filled with whatever its users put into files. Stolen music, perhaps? What we would like is for the final on-disk image of the file system to look like this. To achieve this transition, the file system must perform 3 separate writes to the disk, one for each inode: I brackets v2, bitmap, B bracket v2, and data block db. Note that these writes usually don't happen immediately when the user issues a write system call. Rather, the dirty inode, bitmap, and new data will sit in main memory in the page cache or buffer cache for some time first. Then, when the file system finally decides to write them to disk, after say 5 seconds or 30 seconds, the file system will issue the requisite write request to the disk. Unfortunately, a crash may occur and thus interfere with the updates onto the disk. In particular, if a crash happens after 1 or 2 of these writes have taken place, but not all 3, the file system could be left in a funny state. Crash scenarios. To understand the problem better, let's look at some example crash scenarios. Imagine only a single write succeeds. There are thus 3 possible outcomes, which we list here. First, just the data block db is written to disk. In this case, the data is on disk, but there is no inode that points to it and no bitmap that even says the block is allocated. Thus, it is as if the write never occurred. This case is not a problem at all from the perspective of file system crash consistency. Just the updated inode iv2 is written to disk. In this case, the inode points to the disk address 5, where db was about to be written, but db has not yet been written there. Thus, if we trust that pointer, we will read garbage data from the disk, the old contents of disk address 5. Further, we have a new problem, which we call a file system inconsistency. The on-disk bitmap is telling us that data block 5 has not been allocated, but the inode is saying that it is. The disagreement between the bitmap and the inode is an inconsistency in the data structures of the file system. To use the file system, we must somehow resolve this problem. More on that below. Just the updated bitmap v2 is written to disk. In this case, the bitmap indicates that block 5 is allocated, but there is no inode that points to it. Thus, the file system is inconsistent again. If left unresolved, this write would result in a space leak, as block 5 would never be used by the file system. There are also 3 more crash scenarios in this attempt to write 3 blocks to disk. In these cases, 2 writes succeed and the last one fails. The inode iv2 and bitmap bv2 are written to disk, but not data db. In this case, the file system metadata is completely consistent. The inode has a pointer to block 5. The bitmap indicates that 5 is in use, and thus everything looks okay from the perspective of the file system's metadata. But there is one problem. 5 has garbage in it again. The inode and the data block are written, but not the bitmap. In this case, we have the inode pointing to the correct data on disk, but again have an inconsistency between the inode and the old version of the bitmap. Thus, we once again need to resolve the problem before using the file system. The bitmap and data block are written, but not the inode. In this case, we again have an inconsistency between the inode and the data bitmap. However, even though the block was written and the bitmap indicates its usage, we have no idea which file it belongs to, as no inode points to the file. The crash consistency problem. Hopefully, from these crash scenarios, you can see many problems that can occur to our on-disk file system image because of crashes. We can have inconsistency in file system data structures, we can have space leaks, we can return garbage data to a user, and so forth. What we'd like to do, ideally, is move the file system from one consistent state, e.g. before the file got appended to another atomically, e.g. after the inode, bitmap, and new data block have been written to disk. Unfortunately, we can't do this easily because the disk only commits one write at a time, and crashes or power loss may occur between these updates. We call this general problem the crash consistency problem. We could also call it the consistent update problem. 42.2. Solution number 1, the file system checker. Early file systems took a simple approach to crash consistency. Basically, they decided to let inconsistencies happen and then fix them later when rebooting. A classic example of this lazy approach is found in a tool that does this, FSCK. FSCK is a Unix tool for finding such inconsistencies and repairing them. Similar tools to check and repair a disk partition exist on different systems. Note that such an approach can't fix all problems. Consider, for example, the case above where the file system looks consistent but the inode points to garbage data. The only real goal is to make sure the file system metadata is internally consistent. The tool FSCK operates in a number of phases, as summarized in McCuskey and Kowalski's paper. It is run before the file system is mounted and made available. FSCK assumes that no other file system activity is ongoing while it runs. Once finished, the on-disk file system should be consistent and thus can be made accessible to users. Here is a basic summary of what FSCK does. Superblock. FSCK first checks if the superblock looks reasonable, mostly doing sanity checks, such as making sure the file system size is greater than the number of blocks that have been allocated. Usually the goal of these sanity checks is to find a suspect, corrupt superblock. In this case, the system or administrator may decide to use an alternate copy of the superblock. Free blocks. Next, FSCK scans the inodes, indirect blocks, double indirect blocks, etc. to build an understanding of which blocks are currently allocated within the file system. It uses this knowledge to produce a correct version of the allocation bitmaps. Thus, if there is any inconsistency between bitmaps and inodes, it is resolved by trusting the information within the inodes. The same type of check is performed for all the inodes, making sure that all inodes that look like they're in use are marked as such in the inode bitmaps. Inode state. Each inode is checked for corruption or other problems. For example, FSCK makes sure that each allocated inode has a valid type field, e.g. regular file, directory, symbolic link, etc. If there are problems with the inode fields that are not easily fixed, the inode is considered suspect and cleared by the FSCK. The inode bitmap is correspondingly updated. Inode links. FSCK also verifies the link count of each allocated inode. As you may recall, the link count indicates the number of different directories that contain a reference, i.e. a link, to this particular file. To verify the link count, FSCK scans through the entire directory tree, starting at the root directory, and builds its own link counts for every file and directory in the file system. If there is a mismatch between the newly calculated count and that found within an inode, corrective action must be taken, usually by fixing the count within the inode. If an allocated inode is discovered but no directory refers to it, it is moved to the lost and found directory. Duplicates. FSCK also checks for duplicate pointers, i.e. cases where two different inodes refer to the same block. If one inode is obviously bad, it may be cleared. Alternately, the pointed to block could be copied, thus giving each inode its own copy as desired. Bad blocks. A check for bad block pointers is also performed while scanning through the list of all pointers. A pointer is considered bad if it obviously points to something outside its valid range, e.g., it has an address that refers to a block greater than the partition size. In this case, FSCK can't do anything too intelligent. It just removes or clears the pointer from the inode or indirect block. Directory checks. FSCK does not understand the contents of user files. However, directories hold specifically formatted information created by the file system itself. Thus, FSCK performs additional integrity checks on the contents of each directory, making sure that dot and dot dot are the first entries, and that each inode referred to in a directory entry is allocated, and ensuring that no directory is linked to more than once in the entire hierarchy. As you can see, building a working FSCK requires intricate knowledge of the file system. Making sure such a piece of code works correctly in all cases can be challenging. However, FSCK and similar approaches have a bigger and perhaps more fundamental problem. They are too slow. With a very large disk volume, scanning the entire disk to find all the allocated blocks and read the entire directory tree may take many minutes or hours. Performance of FSCK as disks grew in capacity and RAIDs grew in popularity became prohibitive. At a higher level, the basic premise of FSCK seems just a tad irrational. Consider our example above where just 3 blocks are written to the disk. It is extremely expensive to scan the entire disk to fix problems that occurred during an update of just 3 blocks. This situation is akin to dropping your keys on the floor in your bedroom and then commencing a search of the entire house for keys recovery algorithm, starting in the basement and working your way through every room. It works, but it's wasteful. Thus, as disks and RAIDs grew, researchers and practitioners started to look for other solutions. 42.3. Solution 2, journaling or write-ahead logging. Probably the most popular solution to the consistent update problem is to steal an idea from the world of database management systems. That idea, known as write-ahead logging, was invented to address exactly this type of problem. In file systems, we usually call write-ahead logging journaling for historical reasons. The first file system to do this was Cedar, though many modern file systems use the idea, including Linux ext3 and ext4, Resurf's, IBM's JFS, SGI's XFS, and Windows NTFS. The basic idea is as follows. When updating the disk, before overwriting the structures in place, first write down a little note, somewhere else on the disk in a well-known location, describing what you are about to do. Writing this note is the write-ahead part, and we write it to a structure that we organize as a log, hence write-ahead logging. By writing the note to disk, you are guaranteeing that if a crash takes place during the overwrite of the structures you are updating, you can go back and look at the note you made and try again. Thus, you will know exactly what to fix and how to fix it after a crash, instead of having to scan the entire disk. By design, journaling thus adds a bit of work during updates to greatly reduce the amount of work required during recovery. We'll now describe how Linux ext3, a popular journaling file system, incorporates journaling into the file system. Most of the on-disk structures are identical to Linux ext2, e.g. the disk is divided into block groups, and each block group contains an inode bitmap, data bitmap, inodes, and data blocks. The new key structure is the journal itself, which occupies some small amount of space within the partition on another device. Thus, an ext2 file system without journaling looks like this. Assuming the journal is placed within the same file system image, though sometimes it is placed on a separate device or as a file within the file system, an ext3 file system with a journal looks like this. The real difference is just the presence of the journal and, of course, how it is used. Data journaling. Let's look at a simple example to understand how data journaling works. Data journaling is available as a mode with the Linux ext3 file system from which much of this discussion is based. Say we have our canonical update again where we wish to write the inode, bitmap, and data block to disk again. Before writing them to their final disk locations, we are now first going to write them to the log, aka journal. This is what this will look like in the log. You can see we have written 5 blocks here. The transaction begin, TXB, tells us about this update, including information about the pending updates to the file system, e.g. the final addresses of the blocks I, V2, B, V2, and DB, and some kind of transaction identifier, TID. The middle 3 blocks just contain the exact contents of the blocks themselves. This is known as physical logging, as we are putting the exact physical contents of the update in the journal. An alternate idea, logical logging, puts a more compact logical representation of the update in the journal. E.g., this update wishes to append data block DB to file X, which is a little more complex but can save space in the log and perhaps improve performance. The final blocks, TXE, is a marker of the end of this transaction and will also contain the TID. Once this transaction is safely on disk, we are ready to overwrite the old structures in the file system. This process is called checkpointing. Thus, to checkpoint the file system, i.e. bring it up to date with the pending update in the journal, we issue these writes I, V2, B, V2, and DB to their disk locations as seen above. If these writes complete successfully, we have successfully checkpointed the file system and are basically done. Thus, our initial sequence of operations. 1. Journal write. Write the transaction, including a transaction begin block, all pending data and metadata updates, and a transaction end block to the log. Wait for these writes to complete. 2. Checkpoint. Write the pending metadata and data updates to their final locations in the file system. In our example, we would write txb, iv2, bv2, db, and txe to the journal first. When these writes complete, we would complete the update by checkpointing iv2, bv2, and db to their final locations on disk. Things get a little trickier when a crash occurs during the writes to the journal. Here we are trying to write to the set of blocks in the transaction to disk. One simple way to do this would be to issue each one at a time, waiting each to complete and then issuing the next. However, this is slow. Ideally, we'd like to issue all 5 block writes at once, as this would turn 5 writes into a single sequential write and thus be faster. However, this is unsafe for the following reason. Given such a big write, the disk internally may perform scheduling and complete small pieces of the big write in any order. Thus, the disk internally may 1. Write txb, iv2, bv2, and txe, and only later write db. Unfortunately, if disk loses power between 1 and 2, this is what ends up on disk. Why is this a problem? Well, the transaction looks like a valid transaction. It has a begin and end with matching sequence numbers. Further, the file system can't look at that 4th block and know it is wrong. After all, it is arbitrary user data. Thus, if the system now reboots and runs recovery, it will replay this transaction and ignorantly copy the contents of the garbage block, question mark, to the location where DB is supposed to live. This is bad for arbitrary user data in a file. It is much worse if it happens to a critical piece of the file system, such as the super block, which could render the file system unmountable. To avoid this problem, the file system issues the transactional write in 2 steps. First, it writes all blocks except the txe block to the journal, issuing these writes all at once. When these writes complete, the journal will look something like this, assuming our append workload again. When those writes complete, the file system issues the write of the txe block, thus leaving the journal in this final safe state. An important aspect of this process is the atomically guarantee provided by the disk. It turns out that the disk guarantees that any 512-byte write will either happen or not and never be half-written. Thus, to make sure the write of txe is atomic, one should make it a single 512-byte block. Thus, our current protocol to update the file system, which each of its 3-phase label. 1. Journal write. Write the contents of the transaction, including txb, metadata, and data, to the log. Wait for these writes to complete. Journal commit. When the transaction commit block containing txe to the log, wait for write to complete. Transaction is set to be committed. 3. Checkpoint. Write the contents of the update, metadata, and data to their final on-disk locations. Recovery. Let's now understand how a file system can use the contents of the journal to recover from a crash. A crash may happen at any time during this sequence of updates. If the crash happens before the transaction is written safely to the log, i.e., before step 2 above completes, then our job is easy. The pending update is simply skipped. If the crash happens after the transaction is committed to the log, but before the checkpoint is complete, the file system can recover the update as follows. When the system boots, the file system recovery process will scan the log and look for transactions that have committed to the disk. These transactions are thus replayed in order with the file system again, attempting to write out the blocks in the transaction to their final on-disk locations. This form of logging is one of the simplest forms there is and is called redo logging. By recovering the committed transactions in the journal, the file system ensures that the on-disk structures are consistent and thus can proceed by mounting the file system and readying itself for new requests. Note that it is fine for a crash to happen at any point during checkpointing, even after some of the updates to the final locations of the blocks have completed. In the worst case, some of these updates are simply performed again during recovery. Because recovery is a rare operation, only taking place after an unexpected system crash, a few redundant writes are nothing to worry about. Batching log updates. You may have noticed that the basic protocol could add a lot of extra disk traffic. For example, imagine we create 2 files in a row called File1 and File2 in the same directory. To create one file, one has to update a number of on-disk structures, minimally including the inode bitmap, to allocate a new inode, the newly created inode of the file, the data block of the parent directory containing the new directory entry, and the parent directory inode, which now has a new modification time. With journaling, we logically commit all of this operation to the journal for each of our two file creations because the files are in the same directory, and assuming they even have inodes with the same inode block, this means that if we're not careful, we'll end up writing those same blocks over and over. To remedy this problem, some file systems do not commit each update to disk one at a time, e.g. Linux ext3. Rather, one can buffer all updates into a global transaction. In our example above, when two files are created, the file system just marks the in-memory inode bitmap, inodes of the files, directory data, and directory inodes 30, and adds them to the list of blocks that form the current transaction. When it's finally time to write these blocks to disk, say, after a timeout of 5 seconds, this single global transaction is committed containing all of the updates described above. Thus, by buffering updates, a file system can avoid excessive write traffic to disk in many cases. Making the log finite. We thus have arrived at a basic protocol for updating the file system on disk structures. The file system buffers updates in memory for some time. When it is finally time to write to disk, the file system first carefully writes out the details of the transaction in the journal, aka the write-ahead log. After the transaction is complete, the file system checkpoints those blocks to their final locations on disk. However, the log is of a finite size. If we keep adding transactions to it, as in this figure, it will soon fill. What do you think happens then? Two problems arise when the log becomes full. The first is simpler but less critical. The larger the log, the longer recovery will take, as the recovery process must replay all the transactions within the log in order to recover. The second is more of an issue. When the log is full or nearly full, no further transactions can be committed to the disk, thus making the file system less than useful, i.e. useless. To address these problems, journaling file systems treat the log as a circular data structure, reusing it over and over. This is why the journal is sometimes referred to as a circular log. To do so, the file system must take action sometime after a checkpoint. Specifically, once a transaction has been checkpointed, the file system should free the space it was occupying within the journal, allowing the log space to be reused. There are many ways to achieve this end. For example, you could simply mark the oldest and newest non-checkpointed transactions in a journal superblock. All of their space is free. Here is a graphical depiction. In the journal superblock, not to be confused with the main file system superblock, the journaling system records enough information to know which transactions have not yet been checkpointed, and thus reduces recovery time as well as re-enables use of the log in a circular fashion. And thus we add another step to our basic protocol. 1. Journal write. Write the contents of the transaction containing TXB and the contents of the update to the log. Wait for these writes to complete. 2. Journal commit. Write the transaction commit block containing TXE to the log. Wait for the write to complete. The transaction is now committed. 3. Checkpoint. Write the contents of the update to their final locations within the file system. 4. Free. Some time later, mark the transaction free in the journal by updating the journal superblock. Thus, we have our final data journaling protocol, but there is still a problem. We are writing each data block to the disk twice, which is a heavy cost to pay, especially for something as rare as a system crash. Can you figure out a way to retain consistency without writing data twice? Metadata journaling. Although recovery is now fast, scanning the journal and replaying a few transactions as opposed to scanning the entire disk, normal operation of the file system is slower than we might desire. In particular, for each write to disk, we are now also writing to the journal first, thus doubling write traffic. This doubling is especially painful during sequential write workloads, which now will proceed at half the peak write bandwidth of the drive. Further, between writes to the journal and writes to the main file system, there is a costly seek, which adds noticeable overhead for some workloads. Because of the high cost of writing every data block to the disk twice, people have tried a few different things in order to speed up performance. For example, the mode of journaling we described above is often called data journaling, as in Linux ext3, as it journals all user data in addition to the metadata of the file system. A simpler and more common form of journaling is sometimes called ordered journaling, or just metadata journaling, and it is nearly the same, except that user data is not written to the journal. Thus, when performing the same update as above, the following information would be written to the journal. The data block db previously written to the log would instead be written to the file system proper, avoiding the extra write, given that most I/O traffic to the disk is data. Not writing data twice substantially reduces the I/O load of journaling. The modification does raise an interesting question, though. When should we write data blocks to disk? Let's again consider our example append of a file to understand the problem better. The update consists of 3 blocks, I, v2, b, v2, and db. The first 2 are both metadata and will be logged and then checkpointed. The latter will only be written to the file system once. When should we write db to disk? Does it matter? As it turns out, the ordering of the data write does matter for metadata-only journaling. For example, what if we write db to disk after the transaction containing IV2 and BV2 completes? Unfortunately, this approach has a problem. The file system is consistent, but IV2 may end up pointing to garbage data. Specifically, consider the case where IV2 and BV2 are written, but DB did not make it to disk. The file system will then try to recover. Because DB is not in the log, the file system will replay writes to IV2 and BV2 and produce a consistent file system from the perspective of file system metadata. However, IV2 will be pointing to garbage data, i.e. at whatever was in the slot where DB was headed. To ensure this situation does not arise, some file systems, e.g. Linux ext3, write data blocks of regular files to the disk first, before related metadata is written to disk. Specifically, the protocol is as follows. 1. Data write. Write data to the final location, wait for completion. The wait is optional, see below for details. 2. Journal metadata write. Write the begin block and metadata to the log, wait for writes to complete. 3. Journal commit. Write the transaction commit block containing txe to the log, wait for the write to complete. The transaction including data is now committed. 4. Checkpoint metadata. Write the contents of the metadata update to their final locations within the file system. 5. Free. Later, mark the transaction free in the journal superblock. By forcing the data write first, the file system can guarantee that a pointer will never point to garbage. Indeed, this rule of write the pointed to object before the object that points to it is at the core of crash consistency and is exploited even further by other crash consistency schemes. In most systems, metadata journaling, akin to ordered journaling of ext3, is more popular than full data journaling. For example, Windows NTFS and SGI's XFS both use some form of metadata journaling. Linux ext3 gives you the option of choosing either data ordered or unordered modes. In unordered mode, data can be written at any time. All of these modes keep metadata consistent. They vary in their semantics for data. Finally, note that forcing the data write to complete step 1 before issuing writes to the journal, step 2, is not required for correctness, as indicated in the protocol above. Specifically, it would be fine to concurrently issue writes to data, the transaction begin block, and journal metadata. The only real requirement is that steps 1 and 2 complete before the issuing of the journal commit block, step 3. Tricky case, block reuse. There are some interesting corner cases that make journaling more tricky and thus are worth discussing. A number of them revolve around block reuse. As Stephen Tweedy, one of the main forces behind ext3, said, "What's the hideous part of the file system? It's deleting files. Everything to do with delete is hairy. Everything to do with delete. You have nightmares around what happens if blocks get deleted and then reallocated." This particular example Tweedy gives is as follows. Suppose you are using some form of metadata journaling and thus data blocks for files are not journaled. Let's say you have a directory called foo. The user adds an entry to foo, say by creating a file, and thus the contents of foo, because directories are considered metadata, are written to the log. Assume the location of the foo directory data is block 1000. The log thus contains something like this. At this point, the user deletes everything in the directory and the directory itself, freeing up block 1000 for reuse. Finally, the user creates a new file, say bar, which ends up reusing the same block 1000 that used to belong to foo. The inode of bar is committed to disk, as is the data. Note, however, because metadata journaling is in use, only the inode of bar is committed to the journal. The newly written data in block 1000 in the file bar is not journaled. Now assume a crash occurs and all this information is still in the log. During replay, the recovery process simply replays everything in the log, including the write of directory data in block 1000. The replay thus overwrites the user data in the current file bar with old directory contents. Clearly, this is not a correct recovery action and certainly would be a surprise to the user when reading the file bar. There are a number of solutions for this problem. One could, for example, never reuse blocks until the delete of said blocks is checkpointed out of the journal. What Linux ext3 does instead is to add a new type of record to the journal known as a revoke record. In the case above, deleting the directory would cause a revoke record to be written to the journal. When replaying the journal, the system first scans for such revoke records. Any such revoked data is never replayed, thus avoiding the problem mentioned above. Wrapping up journaling, a timeline. Before ending our discussion of journaling, we summarize the protocols we have discussed, with timelines depicting each of them. Figure 42.1 shows the protocol when journaling data and metadata, whereas Figure 42.2 shows the protocol when journaling only metadata. In each figure, time increases in the downward direction, and each row in the figure shows the logical time that a write can be issued or might complete. For example, in the data journaling protocol, Figure 42.1, the writes of the transaction begin block, TXB, and the contents of the transaction can logically be issued at the same time, and thus can be completed in any order. However, the write to the transaction end block, TXE, must not be issued until said previous writes complete. Similarly, the checkpointing writes to data and metadata blocks cannot begin until the transaction end block has committed. Horizontal dashed lines show where write ordering requirements must be obeyed. A similar timeline is shown for the metadata journaling protocol. Note that the data write can logically be issued at the same time as the writes to the transaction begin and the contents of the journal. However, it must be issued and complete before the transaction end has been issued. Finally, note that the time of completion marked for each write in the timelines is arbitrary. In a real system, completion time is determined by the I/O subsystem, which may reorder writes to improve performance. The only guarantees about ordering that we have are those that must be enforced for protocol correctness and are shown via the horizontal dashed lines in the figures. 42.4, solution number 3, other approaches. We've thus far described two options in keeping file system metadata consistent, a lazy approach based on FSCK and a more active approach known as journaling. However, these are not the only two approaches. One such approach, known as soft updates, was introduced by Ganger and Pat. This approach carefully orders all writes to the file system in order to ensure that the on-disk structures are never left in an inconsistent state. For example, by writing a pointed to data block to disk before the inode that points to it, we can ensure that the inode never points to garbage. Similar rules can be derived for all the structures of the file system. Implementing soft updates can be a challenge, however, whereas the journaling layer described above can be implemented with relatively little knowledge of the exact file system structures. Soft updates requires intricate knowledge of each file system data structure and thus adds a fair amount of complexity to the system. Another approach is known as copy on write, yes, COW, and is used in a number of popular file systems, including Sun's ZFS. This technique never overwrites files or directories in place, and rather it places new updates to previously unused locations on disk. After a number of updates are completed, COW file systems flip the root structure of the file system to include pointers to newly updated structures. Doing so makes keeping the file system consistent straightforward. We'll be learning more about this technique when we discuss the log-structured file system, LFS, in a future chapter. LFS is an early example of a COW. Another approach is one we just developed here at Wisconsin. In this technique, entitled Back Pointer Based Consistency, or BBC, no ordering is enforced between writes. To achieve consistency, an additional back pointer is added to every block in the system. For example, each data block has a reference to the inode to which it belongs. When accessing a file, the file system can determine if the file is consistent by checking if the forward pointer, e.g. the address in the inode or direct block, points to a block that refers back to it. If so, everything must have safely reached disk and thus the file is consistent. If not, the file is inconsistent and an error is returned. By adding back pointers to the file system, a new form of lazy crash consistency can be attained. Finally, we have also explored techniques to reduce the number of times a journal protocol has to wait for disk writes to complete. Entitled Optimistic Crash Consistency, this new approach uses as many writes to disk as possible by using a generalized form of the transaction checksum, and it includes a few other techniques to detect inconsistencies should they arise. For some workloads, these optimistic techniques can improve performance by an order of magnitude. However, to truly function well, a slightly different disk interface is required. 42.5. Summary. We have introduced the problem of crash consistency and discussed various approaches to attacking this problem. The older approach of building a file system checker works, but is likely too slow to recover on modern systems. Thus, many file systems now use journaling. Journaling reduces recovery time from O, size of the disk volume, to O, size of the log, thus speeding recovery substantially after a crash and restart. For this reason, many modern file systems use journaling. We have also seen that journaling can come in many different forms. The most commonly used is ordered metadata journaling, which reduces the amount of traffic to the journal while still preserving reasonable consistency guarantees for both file system metadata and user data. In the end, strong guarantees on user data are probably one of the most important things to provide. Oddly enough, as recent research has shown, this area remains a work in progress.